Yes, where are all the nuclear fusion power plants? Well, in the late 1960s, people were saying, oh, we'll have fusion nuclear power plants in 20 or 30 years. The electricity will be so cheap, we'll almost give it away. What I'd like to do this evening is just lead you through the story of what's been happening in the area of nuclear fusion since then. Now, in 1969, I was a third-year physics undergraduate. Yes, sorry, I have to confess I'm a physicist rather than an engineer by degree. But then I thought, well, nuclear fusion power is the future. That's where I want to be. I want to work in that field. And so I started looking around, and then I discovered just how complicated the maths was associated with plasma physics and magnetic confinement. And so I switched to nuclear fission, and I worked for over 6 years on the design of nuclear reactors for submarines. To be more precise, I was working on the tools that were used for the design. But every 2 years, the MOD would cancel the contract and we'd start on something new. So I decided I'd move to the design of civil power stations. After 2 years, guess what happened? The project was cancelled, and that was the point where I decided to move into industrial process control. And that's really where I stayed until I retired. But nevertheless, I kept a sort of interest in fusion. Just a little watching brief, just to see what happened. I wish I'd made more notes as I went along, to be honest, but I've been trying to follow what's been happening, and it's become, in my view, a little more exciting in recent years. So let's go back to where it all started. And I'll have to, I think, just make sure that everyone is familiar with some of the terminology that's used. So we'll look at some of the basics before we look at the fusion technologies. Not all of them, but some of the basic technologies that people have been trying to use to establish fusion reactions, sustained fusion reactions. For each of those technologies, I'll give a very brief overview of some of the research that's been taking place over the years. Before moving on to what I think is the exciting part, privately owned companies getting involved in nuclear fusion research and development. So again, for each of the technologies, we'll just give some examples of some of the companies and what they're doing. We started, at the beginning we looked at where it started. I'll bring the timeline a little up to date and talk about what's been happening over the past 10 or 20 years. And then, well, a number of people have their views as to how long it will be before we find nuclear fusion power plants. And we'll talk about some of those. Okay, so where did it all start? Well, it was with this man. Einstein, and probably the most famous equation that's ever been written down. Actually, the fourth paper that Einstein published in 1905 didn't have that equation in it. I mean, it's always accredited to him. I think it was more to do with the conservation of momentum in relativistic space, or something like that. But the equations that he did include could be simplified and combined and end up with this equation. And who would have thought that energy and mass were related by the speed of light, or even the square of it? I mean, amazing. Well, that was in 1905, but it wasn't until 1920 that a British physicist, Francis Aston, was able to measure the lighter elements, measure the mass of the lighter elements, and discovered that the constituent parts of the nuclei weighed more than the nuclei that they formed. So there was some mass missing somewhere. About that same time, astrophysicists were trying to work out just how the sun managed to produce so much energy. moving on a little bit, the first fission, now taking, in this case, lithium, firing protons at it from a linear accelerator, caused that nucleus to split into two alpha particles. Alpha particles, if you don't know, they're essentially the helium nuclei, 2 protons, 2 neutrons. And around the 1950s, some Soviet scientists and engineers described what they referred to as the tokamak, a means of trying to produce a machine that would control nuclear fusion reactions and produce power. And in 1956, we have Zeta, the zero-energy thermonuclear apparatus built at Harwell. Now, I've gone a bit too far, really, here. We need to step back a bit. Let's go and look at, sorry, wrong button. Let's go back to basics. Now, we all know that an atom is made up of a nucleus with electrons around it. The nucleus has protons and neutrons in it. The protons are positively charged and the electrons negatively charged. And there's generally an equal number of electrons as protons. Now, of course, that's a simplified schematic diagram. At that scale, the nucleus would be a tiny speck in the middle that you probably couldn't see. And the electrons would be some sort of fuzzy cloud of something around the atom. But that gives the general impression. And it's those electrons that are around the atom that give rise to the chemical properties of the various elements, and thus, as they're organized in a periodic table. And fission, as most of you will know, is taking something, a heavy element, such as uranium-235. So 235 says that's how many nucleons, that's how many neutrons and protons are in there. And the 92 is the number of protons. But if you give it another neutron, it becomes a bit unstable. And it splits up into the two fission products and a load of neutrons. It's not always those particular elements. There's a whole range of different products that can be produced from fission. And of course, you've got all the extra neutrons that can then be used to eventually put a chain reaction in place and get energy out of it. But fusion, which is what we're here to talk about, is taking light elements, banging them together as fast and as hard as you can, so as to join them together. In this case, we've got deuterium and tritium forming a helium nucleus with an extra neutron. Now, if you're not familiar, deuterium, really that's just hydrogen with an extra neutron in. When you hear of heavy water, it's H2O, but the H is deuterium. Tritium is another isotope of hydrogen. It has 2 neutrons. So if you bang those two together, then with any luck, if you've got the conditions right, you'll get some fusion taking place. There's a whole load of different reactions that can take place. Deuterium, tritium is the one up here, but there's lots of others, and I won't bother going through them. But you might be wondering why it is that we can split heavy elements and produce power, or we can bang together light elements and still produce power. And this diagram sort of illustrates it. This is actually what's called the binding energy. So here's the number of nucleons in a nucleus. And this is what they call the binding energy. It's sort of the energy you'd have to expend to pull one of those nucleons out of a nucleus. But it shows that around here, we've got this sort of very stable situation, iron being the most stable. And down here we have uranium, 235 and 238. And you notice that there's a gap, there's an energy difference between the two. Similarly, the light elements, hydrogen down the bottom, and then helium and so on, they also have this gap between the energy and the stable elements. So if you can bang these together and form bigger nuclei, then you're going to get some energy out of it, just as we get energy out of splitting one of these. Okay, one bit of terminology that I'll be using this word plasma quite often. You're all aware, of course, that if you take a solid, you add some energy, it will turn into a liquid, add more energy, it turns into a gas. If you add even more energy, it turns into a plasma. Now you've got to be between 6 and 10,000 degrees Kelvin to get a plasma to form. The plasma really, the atoms are whizzing around so much and colliding into each other, they rip all the electrons off. So you end up with a soup of nuclei and electrons going around. So you've got negatively charged electrons, positively charged nuclei whizzing around, and that's a plasma. And all of the work on fusion depends upon having a plasma in the first place. Okay, let's have a look at some of the technologies. Of course, that's about the only nuclear fusion reactor that we know of and exists at this point in time. But you'll notice that the pressure at the center of the sun, it's pretty big, right? The temperature is, yeah, that's big as well. And there's no way that we can achieve this sort of pressure on the Earth. But we can achieve a lower pressure, but that means that we've got to push the temperature up to 100, 150 million degrees C. So that's what people have been trying to do. And they've used a number of technologies. That these are just a selection. There are others, some of them are combined and there's all sorts of variations. But I've just picked out these as some of the major ones that allow me, hopefully, just to give you a flavour of some of the technologies that are being used. Okay, we'll go through each of these in turn. So, Z-pinch. You're probably aware, if you pass an electric current down some conductor, it produces a magnetic field. So if you have this plasma, this red-pink area, and you pass a current through it, then it generates a magnetic field, and it pulls together the plasma, these positive and negative items that are whizzing around in the plasma. It pulls them together. Pulling them together compresses them so that you get a higher density. They're knocking into each other more often, so you get higher temperature. So the idea is that if you put this, pass a current through the plasma, you should achieve what you want to get the conditions for generating nuclear fusion. They call it Z-pinch because for some reason they decided that the direction of the current was in the Z-axis. But anyway, that's just an aside. Unfortunately, the diagram doesn't go with it. Now, the advantage of this is, of course, it generates its own magnetic field. So you don't need external magnets. So it can be quite a neat little device. I say little, but you know, on the scale of things, it can be fairly compact. A magnetic mirror is a sort of extension of that idea, that if you have your plasma in this bottle or whatever you want to call it, and you put magnets at either end to constrain the plasma, then the plasma starts getting reflected from each end. And it goes backwards and forwards, and there's lots of collisions taking place, and it gets heated. And you can use external magnets to do additional compression of the plasma and hopefully reach the places. Actually, until quite recently, I couldn't find an example of someone using this technology, but I now have, and so there is a slide on it later. Inertial confinement, now this is interesting. This is sort of unbelievable, really. If you think of taking a small, inertial confinement. So when we're talking about magnetically confining, creating magnetic fields to hold the plasma, and this plasma is pretty hot. You know, you can't let it touch material because it will just vaporize the material. So inertial confinement is confining it by pushing it together, physically doing something to it to compress it down so as to get the pressure and the temperature up. So in this case, we have a small gold vessel. Now, as we'll see later, they're about that big, right? And there's a fuel capsule in the middle, so that's only a couple of millimeters in size. And then you direct laser beams inside the gold container. Now, all that does actually is produce X-rays, which then compress the fuel capsule. We'll have an example of that later, and it's even more amazing than that diagram might suggest. There's another type of form of inertial confinement using projectiles. Rather than firing lasers and create X-rays, you actually fire something at high speed at something and bang, you compress it. So we'll look at one of those as well. Now, this is the area where probably most of the research has taken place, magnetic confinement. I mentioned earlier that in the 1950s, in the 1950s, the Soviet scientists had defined what they called a tokamak, a donut-shaped piece of plasma with magnets around it to condense it and contain it and keep it away from the walls of any vessel that it's in. At around the same time, people defined what they called a stellarator. Now, if you think of that donut that's in the middle and you cut it and twist both parts and stick it back together again, then that's the idea. This plasma ring that's going around here has that twist in it. Now, don't ask me why, but apparently that gives you a more stable plasma. But it wasn't until the 2000s that some of the materials that are available and the magnets that were available allowed this to become a reality. Okay, magnetic confinement. Of course, this nice simple diagram doesn't really describe the fact that you've got lots of gubbins to go around it. You've got to get the plasma in, you've got to get hot plasma out, you've got to take that heat out of it and put it through heat exchangers and generate steam and turn turbines. You've got all the things for a power plant. And so, although it's a nice, well, relatively simple concept, you've got a lot of equipment that has to go around it in order to make it actually work. Magnetic target is one I slightly struggle with in terms of understanding the concept. What we have really is a ball of plasma that's in a magnetic field to make it spin and be compressed. And then sorry, yes, I was just trying to remind myself I was going to try and explain this. Once it's spinning and compressed by a magnet, it then is compressed further, either by plasma guns or by physical hydraulic rams. Sounds implausible, but I'll show an example of a couple of those in a while, so hopefully you won't struggle quite as much as I do in looking at it. So the final, that's just an example of using hydraulic rams. You'll notice here, there's the magnetized plasma in the middle. We also have around it what is probably it's molten metal, basically. And it's the hydraulic rams that then force that molten metal in to compress the plasma in the center. And that's just the other variant in terms of the using plasma guns. So again, you've got the magnetized plasma in the center and devices firing bursts of plasma at that to compress it. Okay, the final technology type is called a field reversed configuration. If if you imagine a plasma gun at either end, forming some sort of ball of plasma and then accelerating them with magnets as fast as you can so that they collide in the center, and at the same time as they collide, use strong magnets around it to compress it even further, then the idea is that you reach the temperature and the pressure that's needed to cause fission to occur. The fusion causes the plasma to expand. Charged particles moving creates a magnetic field. Magnetic field induces a current. So it's a concept that would produce electric current directly without having all of that ancillary equipment. So rather than having a reactor of some form and putting it through all of this to be able to produce electricity, by pulsing it, by having pulses of plasma causing pulses of fusion, then you can create the electric current directly. One thing to mention about technology is there isn't really a technology for producing fusion, but something that's used within a number of it. When I mentioned that molten metal, or could be molten salts, around a fuel capsule, then there's something called a breeding blanket. We said that there's a whole range of different types of fusion reaction that can take place. The most popular being deuterium and tritium. Now, deuterium's fairly abundant. I can't remember what the fraction is, but heavy water, the deuterium is separated out, or the heavy hydrogen is separated out to produce heavy water. So we can get our hands on some of that, but tritium is radioactive, and it's a fairly short half-life, 12.3 years. Now that means that after 12.3 years, I've only got half the amount of tritium that I started with. So therefore, there's not much of it around. So the idea is that we have to generate tritium to use as fuel. And that's usually done either using lithium and lead or lithium and beryllium. A little diagram to illustrate that is here. So we have deuterium and tritium. They're banged together, produces a helium nucleus with a spare neutron. In this case, it's captured by a nucleus of beryllium, which gives us helium and two neutrons, sort of double the number of neutrons that we have. And it's those neutrons that go on to be captured by lithium, which then decays into two tritium nuclei. So it's a way of breeding the fuel that you want to use. It also is, by having this blanket around whatever it is you're producing, it can be used as a heat transfer medium. So it will take the heat, absorb the heat from the fusion reaction and take it out to your steam generator through your heat exchangers. Right. Yeah, okay. Research. Let's see what's been happening. If we look at each of those different technologies, we can see what's been happening. Now, by research, I really mean sort of government-funded work. And initially, most of the investigations, most of the research was government-funded. So for each of these in turn, Z-pinch, well, I mentioned Zeta right at the beginning. There was also a device called Scepter. So Zeta was built at Harwell. I think it was about 1957 was the first time that Zeta started operation, but they really didn't get the results that they were expecting. So the theories weren't quite matched by the practicalities. Magnetic mirror. this is something that was produced along with this at the Lawrence Livermore National Laboratory. So early 70s, late 70s, early 80s. So we've got here 2 magnetic mirrors, here a more condensed version, but they really just didn't perform. There wasn't a lot of development of that further. However, the Soviet Union did produce what they called the gas dynamic trap a bit later, in 1986. But again, it didn't really go anywhere. So the idea, if you remember, of taking, putting plasma into a magnetic field and closing off the ends so that the plasma particles reflect off both ends and collide and get hotter and denser, didn't produce the results that people wanted. Inertial confinement. Now we talked about this gold vessel or container, 11.2 millimeters in height, and a tiny couple of millimeter capsule of fuel. So that's deuterium and tritium inside it, and it's compressed by the X-rays that are given off from there. And 192 laser beams were used at the Lawrence Livermore National Laboratory to go into that tiny container. They reached 3 million degrees. That's not bad, but you think, well, perhaps they still have a way to go there. Although in 2022, they did get more energy out of it than they put in, and they have repeated that since then, I believe. So they're making some progress. However, we have that tiny capsule, tiny container in the center, but you need so much more. You need all this equipment to generate the laser beams, and here, this is the target chamber. So that small device is inside there. Now there's a person standing down the bottom there, so you can see the scale of it. And I've yet to find how people propose that you actually get the power out and convert it into electricity. But I'm sure it's been a fantastic research project. If we move on to magnetic confinement, then this is where most of the money has gone. Interestingly, the UK has a fusion energy strategy. I don't know if you can read that, but it says this was published under the 2019 to 2022 Johnson Conservative government. Now I wonder why that's there and whether it's saying, well, don't worry about it. You know, it was just one of the marketing ploys at the time. But nevertheless, a lot of work has been expended on what's called JET, the Joint European Tokamak. That's Culham in the UK. This device, well, it's the world's largest and most advanced tokamak. I mean, it first produced plasma in 1983, so it's been going for quite some while. On last year, in fact, it produced, I've got it down here, 69 megajoules over 5 seconds. Now, I read somewhere that's enough to heat about 4 bars of water, but nevertheless, it's producing power. The Joint European Torus at the moment is being decommissioned and converted to do the next stage of experiments. Another device that's been running at Culham is MAST, the mega amp spherical tokamak, and that's in the process of being upgraded because that's been running for a while as well. But it's called a spherical tokamak because if you think of that toroid that we're talking about, this is in a conventional tokamak like JET. the plasma has that sort of shape. You know, it's a donut shape and fairly thin. But it's been found that if you make it more like an apple with the core removed, then it's a much more efficient and effective and more controllable system. And so there's a lot more research has been going into this spherical tokamak approach. The following project out of the UK is STEP, spherical tokamak for energy production. And that's the key for energy production. You'll notice in this diagram that there's the spherical tokamak, but it's only a small part of the whole design that is actually designed to produce electricity and put it into the grid. So moving to the next stage. It's due for completion in 2040. But they have identified a site in Northamptonshire, I think it is, and they've started surveying the site. In other words, they're starting moving towards the construction process. Of course, lots of other people have been working on magnetic confinement, not just the UK. So I mentioned stellarators early on. So in Germany, there's a device at the Max Planck Institute that is doing magnetic confinement. And during a plasma discharge over 8 minutes, it says there, they produce 1.3 gigajoules. So progress is being made in terms of the stellarator, even though it looks more complicated. I think the advent of superconducting magnets has made the whole process a bit easier. And it's not just Germany, but China have their advanced superconducting tokamak. That's been operational since 2021, and it's getting there, 160 billion degrees C for 20 seconds. That doesn't necessarily mean that they've reached the pressure, the plasma density that they need as well, but certainly they've been getting plasma up into the right realms of temperature. Still on magnetic confinement, India have done a lot. I won't go into some of the details of it, but they've been running for quite a long time. Well, in 2020, this device completed 30 years of operation. So they were quite early into the development of magnetic confinement. Similarly, Japan, they have an interesting fact. At one point, it held the record for what's called the fusion triple product, and I'll come to that later, but it's a means of determining the effectiveness of the plasma, of the fusion process for a particular device. They held the record for that in 2020. They also have what they call the large helical device, which has now been it's been operational since 1998, and that also is a stellarator. So it's like the device that's in Germany, and I think it's the sort of the second largest stellarator that's around. I've put in this work in Italy, that's been done in Italy, not because it's a complete device, but I mentioned that you've got to put plasma in and you've got to get the hot plasma out, and of course it's too hot to touch anything. So how do you do that? Well, the team in Italy are working on the diverter, the device for getting hot plasma out, for the ITER project, and we'll come on to that in just a moment. But basically, there's a whole ring of these around the base of the tokamak. The distance that the plasma has to travel as it's coming out is increased. The volume that it occupies increases, and there's no magnets to compress it. And they have a material that is a tungsten alloy that will survive over 3,400 degrees C. So by using various techniques, they can cool the plasma enough to divert it out using this high temperature alloy, which is actively cooled at the same time. I mentioned ITER in passing, International Thermonuclear Experimental Reactor. It's being built in the south of France. I'm not sure what the original date was for completion. I'm not sure what the original sum of money was, but both have gone up enormously. It's a huge undertaking. You know, it's rather like the current fission power plants that are being built in the UK. Interestingly, these are the members: China, the European Union, India, Japan, Korea, Russia, and the United States. When the UK left the EU, we also had to leave Euratom. So it means that we are no longer part of the team that's working on ITER. Okay, magnetic target. Remember, this is where we take a ball of plasma and then try to compress it. Well, there's not a great deal of research has been done on this. A little in the US, the Los Alamos and at Kirkland, but they're sort of lab scale experiments. And really are just looking to find some of the basic physics, understand the physics better. The pulse field reverse configuration is again, only seems to have been experimented with at the sort of lab scale. And on the website for Princeton here, on their experiments, they said, the experiment probes the dynamics of long pulse, collisionless, low S parameter field reverse configurations formed with odd parity rotating magnetic fields. And hopefully someone can explain to me afterwards what that means, because I just don't know. Okay, so we've looked at some of the technologies, and I'll remind you of them as we go through these, because we'll go through those technologies again and just have a brief look at what is now happening. Because over the past 20 years, and particularly the past 10 years, people have been putting private money into fusion research. Now, if investors are putting money in, then they think there's a good chance of them getting profits out of it. So it must mean that we're reaching a stage where people see it as a reasonable investment. And there's been quite a development of projects, of companies being set up. We'll come on to the numbers later. But if we take Z-pinch, for example, remember this is where you pass a current through the plasma and it induces a magnetic field and squeezes it together. Zap Energy in Seattle, they've, as I said earlier, it doesn't require magnets, but they've produced a design, I believe they're still building it, for pulsing 10 pinches per second. And again, they use this lithium lead blanket to absorb both the neutrons and breed tritium. One thing I forgot to mention about this blanket is, of course, you've got these really high-speed neutrons coming out. Remember, with both fission and fusion, it's the kinetic energy of the bits that result that give you the opportunity to produce heat. In fusion, the neutrons are particularly high energy, going very, very fast. They can do a lot of damage to the materials around. So if you can put a blanket of lithium, something containing lithium around it, not only can it breed tritium, and not only can it be a heat transfer medium, but it can help protect the materials that are beyond it. Magnetic mirror, I mentioned that I hadn't been aware of anyone, any private company following this approach until quite recently. This is a company that was spun out of Wisconsin University. Now, to be honest, all they've done so far is modeled one end of this. Remember, this is where we have plasma in a magnetic confinement, and the ends are essentially closed off so that the plasma is going backwards and forwards, being reflected off the ends, and gradually getting hotter and reaching temperatures and pressures that will produce fusion. Their main target, yes, they've only produced one, a model, a mathematical model of one end of this. Their next stage is to combine two models and then produce a prototype. But they think it'll be 10 years before that prototype is ready and they can actually put it into action. Whereas the previous Z-pinch, if I just have a look, was anticipated to produce 50 megawatts output. Remember that ITER is something like 500 megawatts planned output. The magnetic mirror is 100 megawatts. So they're expecting a little bit more, but it's still an order of magnitude less than something like ITER. Inertial confinement, there's a company called First Light Fusion based up in Oxford. They have this pulsed process. Remember, inertial confinement either compress the plasma using lasers and X-rays, or fire something at it. And these people are using an aluminium projectile. And the different thing about this is that they've designed a capsule, a fuel capsule, that actually amplifies the force that's being provided by this aluminium projectile. Actually, First Light Fusion are giving a talk to the IET next month. It's an online talk where I think they're going to be focusing on this projectile and capsule amplification. They're talking of power outputs in the region of 150 to 400 megawatts. Oh, that's just going through their process of producing the plasma and compressing it and then getting heat out. They do have a design for a full-scale reactor. The thing about all these companies is that they are very good at glossy pictures and very reluctant to tell you any of the details. But it was a nice video that they produced to show how their reactor would actually work. They did actually achieve projectile fusion in 2022. So I think that was the first time that technology had actually resulted in a fusion. They are firing off these projectiles using hydrogen pressure of 10,000 bar. Now, if we come on to magnetic confinement, then there are a whole load of companies. So to start with, there's Tokamak Energy in Oxford. They're using this spherical tokamak design with high temperature superconducting magnets. And they have achieved 100 million degrees Celsius in terms of the plasma density, plasma temperature. But of course it doesn't mention how they're doing with the other things. Their design, they claim, will produce 500 megawatts when it's produced. Fusion technologies, Commonwealth Fusion Technologies, doesn't say up there where they are. I think that's the one that is in Massachusetts. They are building something, so there's photographs of them building something. They have nice pictures of the design, and they're aiming for something like 400 megawatts as an output. They are going through a process of prototypes and gradual refinement. Their next device that they're going to build, they claim will produce sustainable fusion or sustained fusion reactions. On the magnetic target side, remember this is where you've got a ball of plasma and then that's magnetized, so it's compressed and spinning around and then compressed. This is General Fusion, which is a Canadian company. They aim to produce, as I say, break-even conditions by next year. Of course, break-even is not necessarily sufficient to be able to get power out of the system. But they're using deuterium fuel that's compressed and then a liquid lithium liner. And they're using steam-driven pistons to compress that lithium container. Their device is in the process of being built. And they're aiming for about 300 megawatts to get out of that, but whether it will get that far, we have yet to see. Pulsed field reverse configuration, remember where this is you take a ball of plasma at either end and you bang them together as hard as you can and compress them with a magnet. There are a couple of companies that are doing this. In Washington State, there's a company called Helion, and they're hoping to produce electricity in about 3 years' time. Maybe a bit optimistic, but they're using deuterium and tritium, and they're accelerating these balls of plasma to 100 million miles per hour from opposite ends. So it's quite some force to try and bang these two together. And then, of course, they compress them with large magnets. They've reached 100 million degrees C. They have been doing a whole series of prototypes. They're aiming for 50 megawatts, and I think they're on, yes, this particular one is their 6th prototype, and the 8th prototype, and then they're building the 7th prototype, which they should complete this year, and the 8th prototype is planned, and that's where they expect to have something that will actually produce electricity. Remember, with this one, with this technology, when fusion occurs, the plasma expands and pushes back against the magnetic field, and so generates electricity directly. Similarly, in California, there's TAE fusion, and they again have this whole series of prototypes. I think Copernicus, should have been built. Now, the last I looked, it wasn't quite, but it should be completed this year. And then they have their final prototype, except that it's a device that they're hoping will actually produce electricity. So they're moving up in stages. They're 350 to 500 megawatts is what they're doing. Now, interestingly, I think it's them that were, yes, they're using hydrogen and boron as their two elements rather than deuterium and tritium. And they were the first to actually show, to actually get some evidence of fusion from those two forms of fuel. However, I did notice that their Copernicus device is actually running on deuterium and tritium. So perhaps it hasn't worked out quite as they planned. Okay, right. We started there, remember? Our friend Einstein, various bits of physics occurred so as to help understand what might be possible. If we skip now to the other end of the timescale, then this illustrates the number of private industries that have been formed. Now, actually, this goes as far as 2023, and currently, or at least in 2024, there were 47 companies and $7.1 billion invested in those. So it's an expanding field all the time. Now, admittedly, not all of them are aimed at producing power to feed into the grid. Some of them are aimed at providing off-grid power or for producing industrial heat. And some even are smaller devices that are intended for space propulsion. So within that 47, there's a more limited number who are actually looking at producing large-scale power production. But I thought this was quite interesting. If we look here at particle accelerators, this green line, this is the energy that is doubling every 3 years. This is the Large Hadron Collider. If we look at computer processors, then this, which is the number of transistors, has been doubling every 2 years. This plot is this triple product, this measure of performance of fusion devices, and it's been doubling every 1.8 years. That triple product is, if you take the pressure of the density of the plasma, which is equivalent to its pressure, the temperature, and the time at which you can hold it there, multiply those three together, and that's the current measure of effectiveness, of performance to compare the various technologies and devices. But you can see how over time, don't worry about the scale, but it's been increasing markedly in terms of the number of private companies and therefore the amount of private funding that has been going in to fusion research. Okay, where are we going? When will we have commercial PowerPoints? Well, it depends who you ask, basically. This is from, this is about the STEP, the spherical tokamak for energy production, before we actually get to something that can produce power. If we look at the US fusion pilot plant, there's nice pictures of it, but that's it. You know, they haven't got any further. And demo, which is the successor to ITER, is really only at the conceptual design stage. In China, they're a little more bullish. Although their test reactor is still in the design phase, they have something else called Megalab, which they believe will be producing energy within 6 years. If we look at one of the private companies, General Fusion, then they are saying that we'll have power by 2026, or at least break-even equivalent conditions. I've forgotten which one it is, but I think it may be General Fusion who've come to a deal with Microsoft, and that their first device is actually going to be provided to Microsoft to power their data centers. And perhaps this is what I believe from Professor Potter at the University of Cambridge. Commercial fusion power can't realistically be expected before 2050. So it's sort of in line with this, this view. I've bored you for long enough with technology and what people are doing. Now I'll see if I can answer any of your questions, and hope that there's someone in the audience who knows more about them than I do.
So, okay. Thank you, David. Questions?
A lot of the
David,
UK...
will you repeat
yes,
it before?
Yes.
A lot of the UK commercial push that we've had just in the recent years, if you look at some of the websites, they are very optimistic and skimming over the sort of problems and the details that we know exist. I'm kind of worried about this approach because the public are getting bored of lies from scientists, you know.
Yeah, being a scientist, I think scientists and engineers are always fairly optimistic. Politicians, perhaps I shouldn't say it, but I don't think they have a clue. And so they will always take the most optimistic view. And so, yes, we get claims and one-liners, and we as individuals, I think, have to look behind them and find out what the real situation is. Okay.
Question?
Well, whichever the technical solutions comes out first, the problem you have with things like nuclear is it's 20, 30, never years before they build the thing. So when they're saying sort of 2050 viable, does that mean we might get a 13 main output, and then it's going to take another 30 years before they build something viable? And what does the machinery look like compared to a nuclear reactor? How big is it to be something that's viable to power southeastern UK?
Yes, the question was, with the forecast, are we actually going to have usable power plants that deliver power into the grid within the timescales they're talking about, or is it just they're settled on a design? And I wish I could answer it because I don't really know how things were going. I think, well, I've given up thinking that there'll be fusion power plants in my lifetime. So I'm not particularly optimistic. But it could change very easily because some of these new developments, these new startup companies, they're using technology that is quite small. I mean, if you look at ITER, it's like a Sizewell C. You know, it's a big plant. It's a big mammoth engineering project. Whereas some of these devices would almost fit into this lecture theatre. So there is scale there. We could be hopeful that some of these less dramatic attempts at technologies that are slightly simpler and can be built at smaller scale might get us there. Yes, Tom?
What about the comment on the intimidation question? How exactly do you measure 100 million degrees Celsius?
Now that's a good thing for the audience to go away and research and find out how to do that. We know that there are various devices that can be used, mainly looking at the light that's coming out of the devices. So obviously you can't have a physical device there to measure it, but by looking at the radiation that's coming out, you can make various inferences. I don't know exactly how they do it, but I could see that it could be feasible. Yeah.
A question of comparing fission and fusion.
Mm-hmm.
With fission, as far as I understand it, you've got a chain reaction, and the problem you've got is to stop it running away. Okay, so in other words, once you've started a chain reaction, it's kind of self-sustaining, and you kind of control it by keeping your foot on the brake a bit. With fusion, as far as I understand it, you've got to keep on putting in a lot of energy by way of magnetic confinement. So there's a question of how much energy you've got to keep putting into a tokamak to sustain fusion reaction, as opposed to how much you're actually going to get out. So in other words, how efficient is it?
Yeah.
Is that necessarily sort of correct?
Yes, the question is about how much energy you have to put in constantly to get the energy out.
Yeah,
actually, with
fission, you don't have to put that energy in. Once you've got it going, you
well,
don't have to put the energy in.
Actually, even with fission, you have to put energy in because you've got to keep the thing cool, and you've got to extract the heat. So you've got big pumps that are pumping water around all the time, and all the other ancillary equipment.
Yes.
I can't remember the figures, but it's only something like 10% of the output is needed to go back in.
Oh, okay.
So it's quite efficient in that terms. And if I remember the figures correctly, a fission reaction, in other words, splitting one atom of uranium, was something like, gives you 50 million times more power than burning one atom of carbon, right? Fusion gives you 4 or 5 times more than fission. So there's a lot to be gained from using fusion, apart from the fact that you don't have any nuclear waste, that the whole thing is more sort of environmentally friendly.
Right.
There is some sort of waste because you damage material, but it's short-lived. It's a short half-life.
Understand.
Right.
Thank you.
Any more questions? Yes.
I had a question in the sense that, just trying to understand the figures that you mentioned. You mentioned that there were some solutions which were 50 megawatts, and some were 100 megawatt, and then in some of the other things you mentioned also is that they produce heat for about 20 seconds. So when you said 50 megawatts, was it 50 megawatts in those 20 seconds and then nothing for 2 weeks?
No. Interestingly, just as an aside, one of the devices that has been used in a research sense that is a pulsed system, because some of these require pulses of fusion to take place and then use the heat that comes out of that. They've managed to get one pulse every other day, so they have quite a long way to go. But things like the tokamak solution is constantly producing heat, so that you use a conventional heat exchanger to extract that heat. So the figures that have been quoted are intended to be the power output on a continuous basis. That's their target. That's what they're designing the equipment to do.
Target in 2050, the 50 megawatts and 100 megawatts. Okay.
Well, for those devices, and they may come earlier, the larger tokamaks, they're looking at, as I said, for ITER is supposed to produce 500 megawatts.
I was just wondering whether there's any sense in, perhaps, for whenever you go to scale, everything gets about 3,000 times more difficult.
Yeah.
So if you have something about the size of this and have 10 of them, which would now normally, or 100 of them,
Yeah.
occupy the space.
And that's one of the advantages that's been put forward of the spherical tokamak design. One of the companies that's building a spherical tokamak actually state that their device is 40 times smaller than ITER, and yet it's going to produce a similar output.
Interesting.
If a tokamak, say, develops a fault and the plasma is no longer confined, is it going to be expensive?
If it touches any of the sides of the vessel, yes.
Right. So there is a risk.
There is. Most of the work, as I understand it, most of the work has been developing that magnetic containment, that there's the way of holding the magnets together, the magnetic field together, so as to prevent it getting out. One sort of caveat on that is that, of course, as soon as the conditions for fusion are no longer there, the whole thing collapses. So it doesn't run away, it doesn't carry on producing heat. Now it would obviously vaporize some of the material it touched if it got there.
Okay.
Just FYI, AI data centers require about 10 to 500 megawatts. So basically this fusion technology seems to be not sufficient to power AI data centers.
Yes, would these devices be sufficient to power the likes of AI data centers. And I guess you can approach it from various angles. You can say, well, everything's becoming more efficient. So in time, by 2050, the power requirement will be lower. You can say that, you can approach it from the AI side and say, well, they're using large language models which need an awful lot of computing power, but the applications for specific jobs, for particular applications, rather than more general applications, require smaller models and take less power. And you can say, well, a lot of these devices, these proposed fusion devices, could be modular, and you can have several of them, and increase the power available as the size of whatever it is you're powering grows. So that's just off the top of my head. I don't know quite what they're thought of there.
One question for me.
Mm-hmm.
Some of these methods produce neutrons. Neutrons, as I understand it, make metal brittle.
Mm-hmm.
So there's an extra problem with the sort of brittleness. If you run a reactor for a long time, fusion reactor, then the container or something will actually degrade quite seriously if there's high neutron flux. Has that been addressed at all?
Yes. There's been a lot of materials science research going on to provide alloys that are less susceptible. So if you've got something like a tokamak, there is no protection. The plasma's there, the neutrons are coming out, really high energy neutrons, and there's nothing between them and the walls of the vessel. Those technologies that can use a lithium blanket around them, that provides a lot of protection for the materials and gives those other benefits of producing more tritium.
Longer lifetime.
And longer lifetime of the devices, yeah.
Okay. If there are no more questions, then I would like to thank David. And we normally make a little presentation of a certificate and a gift. But David's in charge of the presentation anyway, so you can get me to sign one if you like. Right. But they're only needed to prove that he was here. But I'm sure his family and wife would allow him out on these occasions. But we've had a really very interesting survey of the situation, and I think it's obviously a little bit optimistic in some ways. I'm personally optimistic, and I like to think at least some in the back may be around when this actually comes into fruition. But some of the guys here won't be around at that time. But anyway, I think it is certainly on its way. The other thing which I think has been so nice about this talk is that it has been a combination of science, physics and engineering. It really is a combination of those two, and that's something which I think is very, very commendable, and I think it should continue. And the whole project, I think there was some discussion about whether or not scientists the word used was lie, but actually misrepresents the truth, and it requires an engineer to actually bring them down to earth. But the combination is very powerful. So thank you, David, for very much giving us a glimpse of the future, I think. So thank you, and I'd like you all to show your appreciation.
Thank you much.